Hello dear students, in the sequence of Hankel transform, today we will discuss on application of Hankel transform to boundary value problems. So here is the introductory part of the boundary value problem. Some special type of differential equation will be solved with application of Hankel transform while dealing with the boundary value problem, providing symmetric about the axis. It is convenient to use polar coordinate. It is convenient to use the polar coordinate of the range of the radical variables is 0 to infinity. It can be removed conveniently by the application of Hankel transform. The solution of the resulting equation will be the function of p and remaining variables. This method will be more clear by the following examples. So let us take the example. Apply Hankel transform of zero order to solve the differential equation del square u upon del r square plus 1 by r del u upon del r plus del square u upon del z square equal to 0. Here is the condition 0 less than equal to r less than equal to infinity and z is greater than equal to 0. Satisfying the following conditions, the first condition is u tends to 0 as z tends to infinity and r tends to infinity. And the second is u equal to fr on z equal to 0, r is greater than equal to 0. It is given that u of rz is bounded. So this is the example of application of Hankel transform. See the proof of the example. So proof of the examples, let u of pz denote the Hankel transform of u of rz with respect to r, for which v equal to 0. Therefore, u of pz equal to 0 to infinity u of rz r of j0 of pr dr. Now multiplying the given differential equation by the kernel r of j0 pr and integrating with respect to r from 0 to infinity, we get 0 to infinity del square u upon del r square plus 1 by r del u upon del r of j0 pr dr plus 0 to infinity del square u upon del z square plus r of j0 of pr dr equal to 0. This part is given the differential equation and just we multiply here r of j0 pr dr. Here is the second part of the given statement del square u upon del z square. Here we multiply r of j0 pr dr equal to 0. As we know that 0 to infinity d square f upon dr is dr square plus dx square plus 1 by x df upon dx j0 of pr dx equal to minus p square f. This is the result. We have already had a proof in the form of theorem in the class of second derivatives of Hankel transform. This yield minus p square u plus d square u upon dy square equal to 0. We get the form by using the result this in this equation. We get minus p square f. So minus p square u, because here is the function of the form u. So minus p square u plus d square u upon dx square equal to 0. And multiplying the negative sign, it can be written as d square u upon dy square minus p square u equal to 0, whose solution is u of pz equal to c1 e to the power pz plus c2 e to the power minus pz. You have already learned this part in differential equation. Since u is finite, so u is finite as z tends to infinity. So conveniently c1 equal to 0, otherwise c1 becomes infinite as z tends to infinity. Thus we have the result is u of pz equal to c2 e to the power minus pz. This is equation 1, because c1 e to the power pz becomes the 0. So we have the result u of pz equal to c2 e to the power minus pz. Here is the result. This is equation number 1. Also, on taking the Hankel transform of the order of given boundary conditions, we get u of p0 minus 0 to infinity f r of j0 pr dr j0 pr dr minus fp f r of p. Say this is equation number 2. Now putting z equal to 0 in equation 1 and using equation 2, we get C2 is equivalent to f bar of p. Hence the equation 1 reduced to u of pz equal to f bar of p e to the power minus pz, because the value of C2 becomes f bar of p. Now applying the inversion formula for Hankel transform, we have u of rz equal to 0 to infinity p of j0 pr u of pz dp. So it becomes 0 to infinity p of j0 pr as it is, and this part u of pz becomes, here is the result, f bar of p e to the power minus pz. So here is the final result, f bar of p e to the power minus pz dz, which is the required solution of the application of, in the form of application of Hankel transform. This is the example number 1. We have already discussed the inversion theorem of Hankel transform. Now let us take the another example in the form of application of Hankel transform with boundary value conditions. So this is the second problem of Hankel transform with respect to boundary value condition. Find the potential V of Rz of a field due to flat circular disk of unit radius with center at the origin and axis along the z-axis along the z-axis, and z-axis satisfying the differential equation del square v upon del r square plus 1 by r del v upon del r plus del square v upon del z square equal to 0, and satisfying the boundary value condition, this one v equal to v0 when z equal to 0 and 0 less than equal to r less than equal to 1, and the second condition is del v upon del z equal to 0 when z equal to 0, r is greater than 1. Again we start in the same form. Here is v of pz denote the Hankel transform of v of rt with respect to r, for which this one v of pz equal to 0 to infinity v of rz r of j0 pr dr. Now again we multiplying j0 pr with respect to r, and the limit is 0 to infinity. The integration becomes the first part of integral and second part of integral. The same result we have discussed in the example 1. Now using the result becomes 0 to infinity d square f upon dx square plus 1 by x df upon dx x of j0 px dx equal to minus p square f. This yield the result, and we get the differential equation of the form d square v upon dx dz square minus p square v equal to 0, and we get the general solution of the differential equation v of pz equal to c1 e to the power minus pz plus c2 e to the power minus pz. As usual, we first find the value of c1 and then c2. So by the condition c1 part becomes 0, we get v of pz equal to c2 of e to the power minus pz. This is equation number 1. Now again we applying the inversion theorem, and we get v of rz equal to 0 to infinity c2 of pz e to the power minus pz p of j0 pr dp. This is equation number 2, and del v upon del z is 0 to infinity c2 of p e to the power minus pz minus p square j0 of pr dr. This is equation number 3rd. Now c2p is determined from the dual integral equation obtained, and substituting equation second by and equation third in the given boundary conditions. Thus inverting equation 2 and equation third in the given conditions, we get 0 to infinity p of this part c2 of pz j0 of pr dp equal to v0 for 0 less than equal to r less than 1. This is equation number 4, and 0 to infinity p square c2p j0 pr dp equal to 0. This is equation number 5. On comparing these two parts, we know that 0 to infinity j0 pr sin p divided by p of dp becomes pi by 2. This is equation number 6. And j0 of 0 to infinity j0 of pr sin p dp equal to 0. This is equation number 7. Now comparing equation 4 and 5 with 6 and 7, we get c2 equal to this one, c2p equal to 2 by pi v0 of sin p divided by p square. Now substituting the value of c2 in equation 2, so v of rz becomes 2 v0 divided by pi 0 to infinity e to the power minus pz divided by p j0 of pr sin p dp. This is the required condition of second problem. Similarly, the third problem with respect to boundary value condition of Hankel transform, same problem. This is the form of differential equation del square u upon del r square plus 1 by r del u upon del r equal to 1 by c square del square u upon del t square, and here is the condition u equal to this part u equal to fr, and del u upon del r equal to gr, and t equal to 0, so that this u of rt equal to 0 to infinity p of fp cos of p pct j0 pr dp plus 1 by c 0 to infinity gp sin pct j0 pr dp, where fp and gp are the zero order Hankel transform of fr gr respectively. Similarly, again we start from same as we have already discussed in example 1 and example 2. U of pt becomes 0 to infinity u of rt r of j0 pr dr. Again we multiply the first part of integral and second part of integral using the result same, and we get the differential equation of the form d square u upon dt square, this part whose general equation becomes u of pt equal to a of cos cp